cold temperature. That means, what does it mean, sensing of cold or warm? We don't have those endings are not like typical thermometers we've got at home or outside. They respond to change in temperature. When the temperature goes down below the body temperature, below the standard body temperature, or if they go up. So this is the difference. And we can see that there are some fibers that mostly convey information about cold, and some mostly about warm. And these hot receptors or warm receptors are localized deeper in the skin. Then what we know more, that this sensation, this information about cold or warm, is then conveyed through the through the spinal cord to the brain, and still this cold and warm sensation we can divide into two classes, like, let's say, irrelevant changes or not dangerous for the body. It is called innocuous cold or warm, and that in those that they are recognized as potentially nociceptive, harmful. And as you can see here, this innocuous cold or cold information travels in separated fibers. However, the information about this noxious stimuli may be conveyed in the same, within the same fiber. So this is a difference. And this is like the beginning of some kind of initial conclusion. We've got sensors in the periphery. But what we finally read from the sensors is some kind of job, is the effect of our brain. Because this information is encoded in here in these fibers, and in some way, our brain has learned how to read it. This is so. Let's go. We can see the same separate pathways going into thalamus, even hypothalamus, even to the cortex of insula or even primary sensory cortex. There are a lot of projections here. I will not discuss this. And then we can simply discuss some kind of different types of modality of somatosensation. The first one is free nerve endings, responsible for instance, pain and temperature, as we know. Then we have the specialized structures. They respond to some kind of specific stimuli, mostly mechanical. We can have also some structures that respond primarily to some chemical changes around. So this is how it goes. But finally, this information enters the dorsal horn, and this is the first, not only relay station, it's the first stage of processing and simply integration of that information. Look at that once again about the non-uniform, about the afferent from the nerve endings. We can see here here red fibers, green fibers, blue fibers. What does it mean? Some of them, they are myelinized fibers, like C fibers, or this red and blue. The non-myelinated fibers like blue or red, and simply myelinated fibers, which are A delta in this example fibers. They have different neurotransmitters, and in fact, there's not one neurotransmitters, but a variety of them. So this is the beginning of the story. So still, and then look at that. This is how. This is like a leaflet from the this year Nobel Prize award. What both of them, David Julius and Ardim Pataputian, it is in fact they was born in Lebanon. He was born in Lebanon. He used to live there for more than 30 years, but he was born in an Armenian family, so his background is not easy. By the way, after this Nobel Award, there was celebration in Armenia and in Lebanon. So, and then when he was older than 30 years old, he moved to the USA. This is his story. The other point, David Julius and Ardim Pataputian. I think that they've never worked together. This is so. By the way, they discovered one channel. It's TRP8, but independently. So they worked in and what they discovered? They discovered some channels. And at the very beginning in free nerve endings that can respond to mechanical stimuli or to changing temperature. So this is an example of this TRP channel, which is in here. This is respond to change in temperature, but also to other substances. And this is so-called piezo channel that respond to mechanical force. This knowledge was lacking. We didn't know that before. Why it is of importance? Imagine we have normal neural fibers with resting potential. So it's like it's some kind of hypothetical situation. But there are channels in this in the plasma membrane there, and this channel and those channels have can convey some ions, some cations, calcium, sodium, and potassium. If they are open, calcium or sodium can enter the cell to depolarize the cell and to activate it. Or if not activate, this partial depolarization sensitizes the cells. This is how it works. On the other way, there are some potassium channels that under some conditions can be closed. Normally those potassium channels are open so that in normal conditions slowly but potassium cations can get out the cell. If cations gets out the cell is going, the electrical potential of the cell increases, so it's more negative. It's some kind of desensitization. However, if those channels will be closed, the situation has changed. There is no outflow of cations, so like it is normally, that's why the cell tends to depolarize, to be sensitized. So we've got such a channel modulators in plasma membrane, not only in neural cells, but also in other, but in neural cells, this is of utmost importance. And we have a lot of such large channels in the plasma membrane. However, some of those channels are extremely sensitive to change in temperature or to some chemicals. So these channels which are sensitive to change in temperature, they can open, they can change the conductance by more than 10 or 20 times or even much more than the other channels we know. And this is the case of the discovered channels. So in case of a change of